Yes, thank you very much. And thanks a lot to Winston for inviting me and for organizing this wonderful workshop. Um, I'm not really a philosopher by training, so I come from this to this more as a practitioner of constructive mathematics. But of course, I reflect on what it means to do constructive mathematics, and I will share some reflections on this. Um, I thought it would be good to include some remarks on co-inductive definitions as a counterpoint to all this induction. And I only recently got interested in this because I needed a co-inductive definition in practice, and I couldn't quite figure out how to construct it. So I had to go back to the foundations and think about, well, is it constructible? When are these things acceptable, and so on. Okay, so um, there we go. Okay. Uh, so the particular co-inductive definition I needed is that of the perfect core of a group, which I'll remind you of later, and something very related from homotopy theory, namely the plus construction of pointed type. And so my day-to-day work is in homotopy type theory, where we use type theory to reason about well, all of mathematics really, but in particular with the focus on the homotopy theoretical aspects, higher dimensionality. And so this takes place in the framework of univalent constructive mathematics. So the first part of the talk, I will say a little bit about what univalent mathematics is, because I don't think we've talked about it so far, and not everyone may be familiar. And then also about what constructive mathematics is, and then univalent constructive mathematics is the intersection somehow of these. Then we'll come to the examples above and other examples of co-inductive definitions that I could think of. As I said, co-induction is not my bread and butter, so there may be many more applications of co-induction, but I did think of some to talk about. We'll see then a very interesting feature is that the fundamental ones, I like this distinction that Einstein highlighted from Kleene between fundamental and non-fundamental definitions, but the fundamental co-inductive ones are very easy to construct. There's very little to them. All the difficulty is in the non-fundamental ones. And then it turns out that the best ways we have so far of dealing with these are some axioms which are of dubious constructivity. But it highlights some questions about, well, what does count as constructive after all? So we'll return to this question of constructive mathematics at the end. Okay, so first, a few words about univalent mathematics. So one way of thinking about it is that it's the ultimate expression of extensionality in mathematics. We are only satisfied with the definition of a type of mathematical objects if the corresponding identity type expresses the correct notion of identifications between two elements of the type. We are not satisfied if we just have some other type whose elements we can interpret as expressing being an A, but whose real identity is somehow different. A good example to think about might be real numbers. You can maybe classically you can get real numbers from Cauchy sequences, but the identity of real numbers is not that of Cauchy sequences. So you have to do something. Okay. So maybe you can think about univalent mathematics as mathematics developed with an eye to this structure identity principle that the identity types of structures should be the correct ones. So we can define the notion of a proposition as a type, any two elements of which can be identified. And that is what it means to be a proposition. And then we say a set is a type for which the identity types are propositions. And continuing, we carve out one type, so groupoids, and two types, and so on, but not every type lives somewhere in this hierarchy. There are types that have, but you can take identities of identities of identities, and it's always interesting. There's always some structure there. Okay, so in univalent mathematics, it's crucial that the identity type of the universe, so if you have two types, A and B, we want the identity type to express the correct notion of equivalences from A to B. And this is not going to be a course on homotopy type theory, so I'm not going to define all of these notions, but even above the level of a proposition is that of a contractible type, and that is a proposition that is true. And there's only one true proposition, the unit type. And an equivalence is a function, all of which fibers are contractible. That gives you the inverse map, and it's a homotopically correct notion of equivalence. So Blavatsky proved that if you have this univalence axiom, then you can prove function extensionality, and several other people then showed that you get this structure identity principle for many other types of mathematical objects that you naturally define the type of groups as a set together with a neutral element and a binary operation satisfying the group laws and so on. As a very particular example, you can take the type of sets, which are pairs of a type with evidence that it is a set. And then you get that the identity type of sets is that of isomorphism. So it's fine to look at combinatorial constructions of set, but it's not the notion of set we're usually interested in mathematics, where we identify sets if they are isomorphic, but just different notions of sets. And as I said, so if you want a type of real numbers, it should certainly be the case that identity in the real numbers is the negation of apartness. Apartness being that x is apart from y if it's less than, or if it's positively less than or positively greater than y. Okay. And feel free to interrupt me, ask questions if you'd like. I should say that. Okay, so this is what I take to be some of the goals of univalent mathematics, that you really take extensionality very seriously. And of course, the benefit of this is that any further construction you make with such well-defined mathematical objects will preserve the correct notion of identification. You cannot do a construction on real numbers that doesn't respect the correct notion of identification of real numbers. So you cannot do a set theoretic construction in this notion of sets without it respecting isomorphism. So on. And the only meaningful operations you can do on groups are the ones that respect group isomorphism. So it's also structuralist mathematics. Okay, so this was the univalent part of univalent constructive mathematics. So here's what I take to be constructive mathematics, which I'm a little less clear on, even though I practice it. I take it to mean most basically that we reason by constructing types and their elements. The main question, of course, is then what counts as a construction. You might think that the univalence axiom, saying that the natural map from the identity types of types to the equivalences of types is an equivalence, that is not constructive because it's not immediately, well, you just say, well, why would that be the case? You don't have a construction of that. But we now have, thanks to Thierry and others, good type theories with normalization in which you can construct witnesses for univalence. And there are also other approaches recently towards higher observational type theory, which likewise promises constructions for univalent mathematics. So I take it to be a key, but perhaps not defining feature of constructive mathematics, that we have a collection of constructions for which we have canonicity. This is a more general statement of the existence and disjunction properties of a logic, a first-order logic. It should certainly be the case that if we claim that we have constructed evidence for the existence of something, that and there are no variables, it's a closed term, that this should give us a particular witness for the existence. And if we have constructed evidence for a disjunction, we should know if it's the left or the right disjunct. That's part of being constructive. But it's also should be the case that our means of construction are preserved when we pass to realizability and sheaf models. This expresses as well that our constructions are effective and continuous. Of course, you could achieve canonicity in a classical sense by just making everything a construction. I think that could be done. I haven't thought about it in detail, but I think you could have a way out of getting canonicity if you don't require some more data, some more restrictions of what it counts to be a construction. So if you are realizable in the programming languages, then you can effectively run your construction. And if you can pass to any sheaf model, well, then your constructions are continuous. And those are both intuitions about what it means to be an effective construction. Okay, so for the particular languages we have for univalent mathematics, namely homotopy type theories, we can so far only directly pass to a subtopos model. We know that how to do that in complete generality, and certain internal pre-sheaf models, although there is work to expand that, but still major obstacles remain in order to do the model theory of univalent mathematics inside univalent mathematics. Okay, the basic issue is that we don't know how to construct a good theory of infinity one categories in these languages. Okay. However, if we start with a classical base, we do know how to pass to any higher sheaf topos. That was done by Mike Schulman, and also to cubical realizability models. And I think it's interesting to note that the cubical assemblies models of Umura do not validate that power sets are small. So we can state as the axiom of propositional resizing, that if you have a proposition in a large universe, then it is already equivalent to a proposition in the smallest universe. So I will not talk about this in much detail, but I will tell you how I got interested in co-inductive definitions. So together with some collaborators, I was looking at the study of what is an epimorphism of types. You know that an epimorphism of sets is just a surjection, but an epimorphism of types is much more rarefied. The definition is the same. A map is an epimorphism if for every type X, the precomposition map is an embedding. This means that if you want to extend a map along F, then such extensions are unique. It's the same definition you would give in set theory. And we can still prove that epimorphisms among sets, or from the point of view of sets rather, if you're just caring about sets X, then the epimorphisms are just the surjections. But in general, it's a much more stringent requirement. So let's define a type to be acyclic if its suspension is contractible. And now I will move to the whiteboard and draw a picture of a suspension. Sorry, you can't keep that up. X, the North Pole and South Pole. Identifications. The meridians. So the suspension of a type is a non-recursive inductive construction where you add 2 points as constructors, and then you add path constructors, which are identifications of the North Pole with the South Pole, parameterized by the points of X. And we define a type to be acyclic if this suspension is contractible to a point. And a map is acyclic if all of its fibers are acyclic. Just like we say that a map is a surjection if all of its fibers are inhabited. Okay, so then the result that we proved is that a map is an epimorphism if and only if it is acyclic. So all of its fibers must have this property that when you suspend them, they become contractible. There's also a third condition, which I will use later, which says that it is balanced. And this says that for every surjection into the codomain, the pullback square of F with G is also a push-out. So this means that it looks like it's in the realm of stable homotopy theory. Stable homotopy theory is what you get if you take homotopy types and you enforce that all pullback squares become push-out squares, so that everything becomes linear in a sense. So, yeah.
So, if you want to done, it's not the same as projection.
No, definitely not.
So
every surjection means that the fibers are inhabited. Yeah, and if you're acyclic, then you're also inhabited. That's easy to show. But furthermore, acyclic types must be not just inhabited, but connected. And acyclic types must have a perfect fundamental group. We'll get to perfection on the next slide. Okay, so one thing my collaborators and I would like to do is to construct the factorization of any map as an epimorphism followed by what's called a hypoabelian map. This is analogous to the image factorization of a map as a surjection followed by an embedding. But just now the left map is an epimorphism. So classically, the right factors will be a hypoabelian map. And that's something whose fibers, if you look at the fundamental groups, they have no perfect subgroups. So we call that a group is perfect if the abelianization is trivial. In other words, if every element is a commutator. Okay. So if we want to construct this factorization, we need to construct, first of all, the perfect core of a group. So we look at, if we want this this factorization, well, we can first take a connected cover because we're looking for something acyclic, so we must have something connected. We have a connected type, and then its fundamental group might not be perfect, but we want to mod out by its perfect core. So we need to construct for every group as part of this endeavor the perfect core, which is the largest perfect subgroup. So classically, it's easily definable as the intersection of the transfinite derived series, where you iterate the formation of the commutator subgroup. So you start with the group itself, you form its commutator subgroup, the commutators of the commutators, and so on. And this doesn't terminate necessarily in omega n steps. In fact, Malchev proved that any ordinal is a stabilization ordinal of the transfinite derived series. And if you start with a countable ordinal, you can take the group to be countable. So this suggests that it might not be so easy to construct this, even though we are somehow looking at a very simple operator, not on families of types over the group elements, but just the families of propositions. Related to so what we actually want is this further construction, the plus construction. This was classically done by Quillen in classical homotopy theory for the purposes of algebraic K-theory. And this is what you get if you want to take this factorization of the terminal map from X to a point of an acyclic map followed by a hypoabelian map. And as I said, it's important for algebraic K-theory. For a ring R, the homotopy groups of this plus construction of BGL of R. BGL of R is itself an inductive construction. You take the, I guess you take the finitely presented R modules, something like that, and you stabilize under adding a trivial copy of R to make a connected type. So there's an infinite co-limit of the general linear groups of R, and you have this classifying type, and you form its plus construction, and this gives you a new homotopy type that carries all the information of algebraic K-theory of a ring. Okay. So the point is, if we have a pointed type X, and we want this plus construction, the fiber is going to be an acyclic type because the acyclic maps are stable under both pullback and pushout. So if you take this pullback, then F will be an acyclic type. And because of the balance property, it'll be the largest acyclic type that maps to X. So this is a coinductive flavor of a construction. And we also have a conjecture that it's the terminal co-algebra of a particular operation, taking the fiber of the identity type north equals north in the suspension of a type that maps to X. So this is the loop suspension Y. Just as an aside, on the level of classifying types, this loop space of a suspension implements the abelianization. So this is a homotopical version of abelianizing or finding the commutator subgroup. Okay. So now let me come to the some other examples of co-inductive definitions that I could think about. So we saw yesterday a lot that we define inductive types by some constructors that build elements of them, possibly from parameters or from previously constructed elements. Dually, if you have a co-inductively defined type, we determine it by the destructors, which are observations that are possible if you have an element of the co-inductively defined type. The most basic example is that of a function type. The observations you can make on a function are the applications of an input. So I think, Anston, you said that we take the universe to be formed by inductive types, but we also have at least one co-inductive type, namely the function types. Another example is the co-natural numbers. Co-natural numbers has an observation we can make on it that tells us whether it's zero or the successor of another co-natural number. And more generally, you can do streams over any type. And for a stream, we can observe the head, which is an element, and a tail, which is another stream that we can continue the process with. More general still, you can do non-well-founded trees. So these are called M types because they are upside down W types. They're non-well-founded trees. And if you have an M type, an element such a non-well-founded tree, then its shape will be an element of the type A. And for every element of B of this shape, you get a subtree indexed by that. Maybe a little classical, Peter Fried observed that you can define the real interval co-inductively. You must assume that you're working in a slightly different, not just in the bare types, but you have strictly bipointed objects. So you have a 0 and a 1 that are different. And then if you have such an element of the co-inductive unit interval, the observation you can make is that the splitting of it is an element of the push out of two copies of the interval put side by side. So you know that you're either on the left half, on the right half, or you're both, but then you're at the endpoints. Okay. To make this work constructive, we probably would need some kind of analytic LLPO to make it equivalent to the actual unit interval. Further applications of co-induction include modeling behavior of physical or computational systems. You can imagine the case of automata, which have observations done on them. You push a button and you get a new state of your automaton and maybe some other observation that comes out. It lights up an LED or something like this. And then you can push another button and you get a new state and so on. And co-inductively, you would have the type of all traces of these, which would cover all possible behaviors of such an automaton. But that could be not just deterministic automata, it could be non-deterministic, some kind of quantum system, other physical systems where you might have some kind of topological dynamics. Maybe you have a system of differential equations that evolve a system, and you could give a co-inductive treatment of this. It's not really something I know much about, but it's something that is within the realm of co-induction. Of course, maybe something that you do know about is non-well-founded set theory, as proposed by Peter Axel, and we will come back to some things that Peter Axel came up with later on. And there are co-inductive semantics of various kinds of modal logic having to do with describing the modal behavior of this kind of behavior of systems. Like, will the machine eventually turn on the blue LED if I keep pushing this button, or will it always have this state that has some observable property? That kind of thing. Okay. So let's talk about the most kind of fundamental co-inductive definitions you can make. And these are the terminal co-algebras for polynomial functors. So the polynomial functors between families of types indexed by some particular type, so types indexed by a type I or J, they are the functors you can get by taking some mixture of substitutions, sums, and products. And by distributing the sums of the products, you can always assume that they have this form. So the polynomial applied to a type family over I is a type family over J, which over J gives you the type of the sums of some B's, such that for every E's and some other type, depending on that, gives you an element of X um, of, of some input index. So these are given by a diagram that looks like this. You have two other types, E and B, and you have maps from B to J and E to I, and you have a map from E to B. So we also need to know that an analytic functor or finitary functor is one for which all the fibers are finite sets. And this means that all these types we take the product over are finite types. So you can think of these as infinite sums of finite monomials. And now the W types that are quite general are the index W types, and they're just the initial algebras for polynomial endofunctors, so functors where the I and the J coincide. Okay. So if you want a fundamental coinductive type, it's natural to say that these are the terminal coalgebras for polynomial endofunctors. And these cover many of the examples we had before, including streams and M types and indexed M types and so on. And you don't need any fancy machinery to have them. You can just construct them from the natural numbers, because all of these polynomial functors, if you just take them like that, they're omega continuous. They preserve limits of an omega sequence. So you just start with the terminal object in the types over I, which is I itself with the identity map. And then you apply P to that, since it's a functor that has an arrow to the terminal object, and you apply the functor again, and then you get an omega sequence, and you take the limit, and that's the M type. That's the terminal coalgebra. So you don't need anything at all for these fundamental coinductive types. And this is in stark contrast to the case of W types, where, of course, you require these the strength of iterated inductive definitions plus or minus, depending on how strong your universes are. Okay. So alas, what I want is this perfect core, which is not a fundamental coinductive type, because it's not just a sum of products. It's a truncated sum of products, right? In the perfect core, I'm starting with a subset, and I take the commutators that are be formed by this subset. So it's I need to express my element as some product of commutators, but I only need to know that there exists such a product. But actually, what I have is a finite list, two finite lists of group elements, and an equation that X is this product of the commutators of elements taken from these lists. So it's a completely finitely accessible functor, but now I truncate it at the end. So this is no longer one of these fundamental ones. And in fact, you do this tiny little thing, and it's no longer omega continuous. So this is also in this analogy with the case of inductive types. If you have an inductive, if you look at a polynomial, and it need not be omega co-continuous, but if it's finitary, then it is omega co-continuous, and you can form the W type just by taking the sequential co-limit dual to what I had before. And if you truncate, then it's still omega co-continuous. In fact, if it's kappa co-continuous, then truncating it will still be kappa co-continuous. But no such luck for the greatest fixed points, for continuity rather than co-continuity. However, it's not so hard to see that. So we have the M type of the untruncated polynomial, and we could, of course, try to guess that maybe the greatest fixed point is just what you get if you take the image of that. So you truncate, just like, well, so this would, for the perfect core, this would say an element of this limit would be an infinite tree that says, well, your group element is this product of commutators, and then for each of those you have an expression as a product of commutators, and they are expressed as a product of commutators, and you have an infinite tree. And maybe you just say, well, there exists such an infinite structure. And then this is indeed the greatest fixed points if you have dependent choice. You can pick, if you only have, if you have, I won't do it right now, but if you sit down with a piece of paper, it's the natural thing to do. You just need dependent choice. So Peter Axel had the same problem modeling non-well-founded constructions. And I guess that you cannot do without something, because he isolated a slightly weaker principle that he's called the relation reflection scheme. And this still suffices to make this the greatest fixed point. So the relation reflection scheme says that if you have a large total relation and an element in the ground universe of the relation, then there exists already a small subset that is closed under this total relation. So this is not something that you can expect to construct necessarily, but it does have this curious feature that it is stable under passage to sheaves and to realizability models. So Peter showed this in the case of sheaves on complete hiding algebras, and then Albert Ziegler, who is a student of Wilfried Buchholtz, by the way, showed more generally that it's preserved by passage to sheaves and applicative topologies. And I didn't know this notion of applicative topologies. It seems quite interesting. It's a common generalization of realizability and a sheaf model, at least for the case of one toposis. So as another side question here is there some version of this that would work for higher toposes? Maybe. In any case, I do conjecture that we do know how to make sense of higher toposes, and if we had the model theory of univalent type theories and univalent mathematics, then this would still be stable under passage to sheaf models. Let me just emphasize, in case the point was not forceful enough. So if you look at this if you truncate this polynomial, if you take this polynomial for the perfect core and you truncate it, then you have to iterate maybe along an arbitrary ordinal in order to get to the fixed point. However, assuming a very weak principle, you can just iterate the untruncated polynomial omega many times and then truncate, and then you already get to the fixed point. That's quite remarkable, I think. Okay. So here is a comparison with the situation with inductive type. So not going beyond the realm of polynomial functors. So there's an infinitary algebraic theory for which ZF itself doesn't prove the existence of an initial algebra by Andreas Blas. And then Peter Lumsden and Mike Schulman converted this to a higher inductive type. So a higher inductive type is an inductive type where you do not only have constructors, but you also have these path constructors like we saw in the suspension. So you cannot expect to have these higher inductive types even in a quite strong classical system without choice. But there's a very weak notion of choice that allows you to construct these higher inductive types, namely the axiom WISC, or sometimes called the axiom of multiple choice. WISC stands for weakly initial set of covers. So it says that for any small set, there is a set of surjections onto it, such that for any surjection, it factors through one of the ones in your small collection of covers. So for this particular infinitary algebraic theory, and also many other higher inductive types, but particularly the kind known as quotient inductive types, which are the kind of higher inductive types you'd be interested in, even if you're only doing set level mathematics. You can construct them with the axiom WISC. And I should say that WISC shares with RRS this feature of being preserved by passage to a realizability model or to a sheaf model. And it follows from a kind of choice principle that you would have in an intentional setup, an intentional system. Okay. So here are the questions that I would like to think about in regards to this. So what actually counts as constructive? So we looked at these principles, the relation reflection scheme and the weakly initial set of covers, and they do have this strong invariance property that they are preserved by most of the known constructions of models of constructive theories, sheaf and realizability models. However, they're clearly not something that you can get canonicity for just by themselves. If you just add by fiat a construction for this weakly initial set of cover, there's no way to provide a term that witnesses the existence of this weakly initial set of covers. Or if you look at the relation reflection scheme, there's no canonical choice for the small reflection of the large relation. However, it does suggest that there might be other constructions that we are not aware of or that we haven't thought about that would imply these principles, that would give you a larger calculus that would still have canonicity from which you could construct these. Or it could at least be the case that forever, of all the mathematical uses we want to put these principles to, we could construct them with something that would count generally as constructible. Yeah, now, in particular, I'm interested in this question whether the perfect core is definable in, say, Martinov type theory with univalence axiom and some higher inductive types. So finally, I want to mention that in this new development called higher observational type theory, this has the feature together with cubical type theory that co-inductive types have the correct identity types by default. So you get this bisimulation principles very neatly. And there, co-inductive definitions actually play a key role in defining the system itself because you need them for defining the observational identity types for the universe. And then another intriguing aspect is that, well, we have this problem of doing the model theory of univalent theories in univalent mathematics, and because we don't know how to construct higher category theory, and higher category theory could be constructed if you knew how to define what are called semi-simplicial types, never mind precisely what they are, but they do have a co-inductive definition in some slightly different type theories. There's something called display type theory, due to Mike Schulman and Astra Kolomatskaya. And there they have a very simple co-inductive definition. Again, it's not a co-inductive definition of this polynomial sort, but maybe we need to be more open-minded about what counts as an observation that you can do in the destructor of a co-inductively defined type. And finally, so higher topos theory, which is somehow what is being probed by the constructive univalent mathematics, it does rhyme a lot with predicativity, because even if you're a completely classical mathematician, you have the sequence of object classifiers or universes, which in contradistinction to subobject classifiers don't have any kind of claim to being completely universal. In a subobject classifier, in a classical topos theory, you classify all subobjects. But for the object classifier, it's just inconsistent to assume that you have object classifiers. So you have to do some things in a kind of predicatively minded way. But it would be very nice if we also had mathematical uses of predicativity, even at the level of propositions. And maybe we could get those if we could come up with some other model constructions, or maybe we could make use of the increased invariance that we get from predicative constructions. Okay, I'll stop here, but we'll have time for questions.